Now, you may be asking at this point, well, why do we care? Very nice, but why do we care about this? Well, it turns out in equation systems, if you look at the column vectors of your coefficient matrix, you can interpret those as being vectors. Each column of that coefficient matrix can be considered a vector. So if you have a 3 by 3 matrix, you'd have three 3 by 1 vectors. It turns out if those columns of your coefficient matrix are linearly dependent, then that means you will not get a unique solution to your equation system. However, if those column vectors of your coefficient matrix are linearly independent, then that means you will get a unique solution to your equation system. So that's primarily why we're interested in this concept. Let me give you a simple illustration. Consider this simple equation. x1 plus 2x2 equals 3. And our next equation is 2x1 plus 4x2 equals 7. Now, for this equation system, what is the coefficient matrix? What's the coefficient matrix? Okay. The first row would just be 1, 2. The second row, 2, 4. Suppose you consider these two column vectors. V1 equals 1, 2. V2 equals 2, 4. What's true about these column vectors? They're linearly dependent because V2 is just 2 times V1. So what that means is this coefficient matrix is said then to be singular because the column vectors of the matrix are linearly dependent. And we're going to see what that means is if you try to solve this equation system, in this particular case, you get no solution at all. And to see why, let's just use the substitution method to try and solve this equation system. From that first equation, I could write x1 equals 3 minus 2x2. Now, substitute this result into the second equation. 2, notice that the second equation is 2x1 plus 4x2 equals 7. Substitute into that x1 in the second equation. 3 minus 2x2. Okay, we're just substituting for x1 in this equation right here. Okay. Plus 4x2 equals 7. Now we have one equation in one variable, x2. So let's try to solve this. We would get 6 minus 4x2 plus 4x2 equals 7, or we get 6 equals 7. Obviously, 6 does not equal 7, does it? So what does this mean when you get a nonsensical result like this? What does it mean, Jonna? There's no solution. See, we assumed when you try to solve an equation system like this, you assume that there are values of x1 and x2 that will simultaneously satisfy both equations. You are assuming that. But in this case, that assumption doesn't hold. See, we got 6 equals 7. That's not true. So that means one of our assumptions we made is wrong. And the assumption we made is that we could simultaneously satisfy both equations. Okay. This is what happens when the column vectors of the coefficient matrix are linearly dependent. You either get no solution, which is what we got in this case, or you get an infinite number of solutions. To show the case where you get an infinite number of solutions, let me just change this from a 7 to a 6. And then you intuitively look at these two equations. What is true about these two equations? Right. If we just multiply the first equation by 2, Helen, we get the second equation. So really what we have in this case, really we just have one equation and two unknowns. We just really have one equation and two unknowns. So any values for x1 and x2 that satisfies the first will also satisfy the second. Okay. And so in this case, we get an infinite number of solutions. Now, had you tried, maybe you didn't spot this when you first looked at the equations, so you try to solve it by elimination of variables. Here's what you'd get. x1 equals 3 minus 2x2. That's the same. The second equation, when we substitute in for x1, however, this left-hand side is the same, but right here we get a 6. Are you all with me? We're just doing the same thing. We're resolving this system by elimination of variables. And this would be a 6 here. And now what do we get? The minus 4 and the plus 4 cancels out. We get 6 equals 6. That's true. 6 does equal 6. But it doesn't help us solve the system. Actually, the way to look at the solution in this case is there are an infinite number of solutions. Any pair of values of x1 and x2 that satisfy the first equation will be a solution. So the solutions just look like the graph of this equation. The solutions are any point along this line. Let's measure x1 along the horizontal axis and x2 along the vertical axis. Then I could rewrite this first equation this way. 2x2 equals 3 minus x1. Divide both sides by 2, and you get x2 equals 1.5 minus 1/2 x1. Graphing this equation, it just looks like this. Vertical intercept 1.5, the slope is minus 1/2, so it's a straight line that looks like this. Any point along this line that satisfies this equation will also satisfy this equation. And of course, there are an infinite number of points along any line, so there's really an infinite number of solutions. Okay. So this is why we're interested really in this concept of linear dependence and independence, because it will help determine whether or not we have a unique solution to the equation system, or whether there's any solution, or maybe an infinite number of solutions.